Morning. See, we got people still logging in, so we'll wait a couple of minutes before we get started. While we're waiting, does anybody have any questions about anything?
No, sir. How have you been, doctor?
All right, we're gonna uh-oh. Yeah, we got over half people here, so we're gonna go ahead and get started. All right, today we are between today and tomorrow, we're gonna finish this short section on conversion of alcohols to alkyl halides. So conversions of alcohols to alkyl halides. That's the umbrella that we're working under. And hopefully you had a chance to watch the videos that I sent, because we're going to jump right into the mechanism of these reactions and how they work. All of these reactions are substitution reactions. Right? All of them are substitutions. The type of substitution is going to vary. Some of them are, well, we're looking at three mechanisms. Two of them are going to be SN2 type, and then one is SN1 type. All right, SN2, if you remember from part one, and we're going to study this in more detail even in part two, but it's a concerted, one second, I got sweat on my iPad. And then SN1 is stepwise. The substitution step is stepwise. Right, so we'll talk about that when we look at the actual mechanism. So you got all of these are substitutions. They are either SN2 or SN1 type substitutions, which we touched on briefly in part one. If you took I'm not sure if Abdallah covered it or not, but I think he did, and I know I did. So if you took part one from me, you should definitely be familiar with the what's SN2, SN1, and we're going to talk about it, but I just want to make sure that we're all on the same page. And then another thing about these reactions is that OH has to be converted, excuse me, into a better leaving group. Right? OH by itself is a bad leaving group. And the way you judge, and I'm just jumping ahead to these substitution reactions, the way you judge a leaving group is by looking at the pKa of its conjugate acid. So for OH, the conjugate acid is water, right? All the conjugate acid is the conjugate base plus a proton. If you remember the acid-base chemistry that we learned in part 1, right? So in order, if I was doing a simple reaction with OH as my leaving group, it would leave as, if I was doing a substitution, it would leave as, let's just say I'm doing this. Right, it will leave as the hydroxide anion. And this is a very poor leaving group. Anybody remember with acid-base chemistry, let me think. Yeah, so with acid-base chemistry, when we talked about conjugate acids, conjugate bases, how do we determine the quality of a conjugate base, whether it was or the quality of an acid? How do we determine that? Like a strong acid versus a weak acid? Anybody?
Is it like a low pK?
I keep forgetting it's Monday. All right. So that leaving group is based at the idea behind the leaving group and whether it being good or bad is based on the same premise as the conjugate base. All right, I see something in the chat. Okay, all right. Yeah, that's kind of a circular. So the conjugate base and the leaving group are comparable. We can judge them based on the same criteria. So for the leaving group, we say it's a good leaving group when it's stabilized. All right. So what that means is that if it's stabilized by, there were 5 things we learned in part 1, at least in my section, we learned in part 1, right? Hybridization, induction, resonance, electronegativity, and size. Right. So those same factors come into play when we talk about the leaving group. That's why we say that we can look at the pKa of the conjugate acid and determine whether it's a good or bad leaving group. All right. So let's jump in. Right. Remember, again, these are the things we kind of go in with as our tools to gauge and analyze these reactions. And they're also going to answer questions as to why we do what we do and the mechanism. So all of these are substitutions. So we're going to be swapping out OH for a halogen, right, to convert an alcohol into an alkyl halide. They're all going to be either SN2 or SN1 type substitution in that substitution step. And then we have to make the OH into a better leaving group. All right, so hopefully you had a chance. That video was not very long either. So hopefully you had a chance to either watch that or read the section on this topic that's listed in the syllabus, because we're gonna jump right in and look at the mechanism. So I want to start out with the easiest mechanism. So we're going to start here. Right, and let me go back up here. We're going to talk about 3 methods. There are multiple methods, but we're only going to talk about 3. And then this is my abbreviation for alcohol, ROH. We'll talk about addition of HX, or X is a halogen. We're going to talk about use of PBr3. That's the second easiest mechanism. And the hardest one is going to be thionyl chloride. So we'll save that one for last. Right. So thionyl chloride, PBr3, those are 3 methods. So don't, if you have problems with like reactions and trying to understand like what's happening, all of these, when I say addition of HX, those are my reagents that are used to convert the alcohol into the alkyl halide. So all of these reagents are just tools that are used for that conversion, right? And it's depending on what I want. If I want a chlorine in the place of alcohol, then I'm not going to use PBr3, right? I'm going to use some type of reagent that has chlorine as one of the reactants that does the substitution, right? If I want to put bromine, then I'll use PBr3 or something like that. So let's jump into the first mechanism right here. Hopefully you had a chance to download this handout as well. So this is addition of HX, where X is a halogen. Again, X equals chlorine. Let me do them in order. Bromine or iodine, right? Those are my 3 most typical halogens that I use for this method. Right, fluorine, it does not work. It's bound too tightly to the proton, and so it's difficult to use that because it's not a very good acid. Even though you would think it is, because of fluorine's electronegativity, it's just not a good acid because the HF bond is really tight and short, so it doesn't give up that proton readily. All right. Whereas if you compare HCl, HBr, HI, they're bigger atoms, wider atomic radius, and so the let's say for instance HCl, the HCl bond is much longer and it's easier for that to donate that proton. Plus, the conjugate base is more stable because it's on a larger atom spread out over a larger surface area. All right. So how am I going to do this? Well, the first thing I have to do is make OH a better leaving group. We already said it's a poor leaving group. Right. That's the first step. So when you see the step going from here, where I have OH plus HI, right? Notice the intermediate here, I have a hydronium ion. When you see water like that with a plus charge as a leaving group, call it a hydronium. You're going to see that a lot. So that's why I'm giving you the terminology now. So when you see it again, it doesn't confuse you. All right. So we make OH a better leaving group. One way to do that is what? Somebody tell me what where that hydronium intermediate came from.
The oxygen attacked the hydrogen from the HI.
In terms of volume up and make sure I'm not by myself. Was somebody saying something or no?
I said that the oxygen kind of attacked the hydrogen from the HI, and then
What's that? Yes, very good. What do we call that process? When we give a proton up or an atom picks up a proton from an acid, what do we call that?
Like
Deprotonation.
Okay, deprotonation, good, or proton transfer, very good. So we can call it proton transfer or deprotonation. Good. Right? That's the first step. And the first step is to do what? Make OH a better leaving group. OH by itself is poor. If you look up the pK for water, it's somewhere around 15 or 16. You look up the pKa for the hydronium ion, which is H3O plus. I think it's -1 or -2 or something like that. Somebody look that up. Look up the pKa H3O plus. Or you can just type in hydronium. Right, so in order for me to pick that proton up, that oxygen has to donate a pair of electrons to the acid. And then this has 3 lone pairs on it already. So I'm breaking the HI bond. This is simple acid-base chemistry, right? And that step gives me the hydronium intermediate. Did anybody find that pK? It's in the chat. I saw something in the chat. All right, so the hydronium is a much better leaving group. First of all, when it leaves, it's going to be neutral. Second of all, when it leaves, you're going to also give that oxygen a pair of electrons and quench that positive charge, right? So when this leaves, it leaves like so. I'm breaking the CO bond and I'm giving those electrons to oxygen. So over here, it'll be this plus H2O plus I minus. Right, any questions about that? Right, if I break a bond between 2 atoms, like I just did, what kind of bond cleavage is that from part 1? We learned that in part 1. It's either homo or hetero, and it's either lytic or genic. So which one is it? Where one atom takes both electrons.
Heterolytic.
It's heterolytic, good. I'm gonna write it out, H, like so, all right? So now we go from this intermediate to a carbocation intermediate. And that brings up another point about this reaction, right? It is specific, this method or technique specific for tertiary and secondary alcohols, right? For that reason, the fact that it goes through a carbocation intermediate is specific for those types of alcohols. Tertiary, this is a secondary alcohol, but this method is specific for tertiary and secondary. Can somebody tell me why? What is it about the cation that you form when you lose your leaving group? What is it about that cation that would require, or that the substitution pattern would facilitate, like, or would make better? What is it? What do you think? This is all part 1, second week, part 1. I'm making a cation. What's the stability trend? Anybody? For cations? What's the most stable cation that you can make? I'm gonna stop asking questions. Go ahead.
Tertiary.
Tertiary, good. Right? Tertiary cation is more stable than the secondary, which is more stable than a primary. right? Tertiary, a tertiary cation, let me put that over here, will be something like this, right? And then the secondary would be like something like that, which is what we have up top. And the primary would be something like this. With the plus charges on the primary carbon. All right. I'm putting lunch on the line for this next question. Why is the tertiary more stable? What is it about the tertiary that makes it more stable as a cation now?
Does it have to do with like hybridization, maybe?
Well, no, because they're all going to be sp2 hybridized. It's something more like more obvious than the hybridization state.
Would it be are we talking about the bonds, like the carbon-hydrogen bond?
Or the carbon-carbon bond. Like
Yep.
right here, here, and
Yeah.
here. All right. So it does kind of, the hybridization state does have some role, but the carbon is a full positive. So it's going to pull electron density towards itself, right? And these carbon-carbon bonds are electron rich. So the more you have around the charge, the more stable it is. It's stabilized by a process what we call I mentioned this the other day, I think.
Conjugation.
Conjugation. Yep. Who was that, by the way?
Morgan Banks.
All right. Put your cash app in the chat, because your answer was very accurate. It's the bonds around it, and they're stabilizing that charge. All right. So you can see going to a secondary, you lose a carbon-carbon bond. So you're going to lose a measure of stability, even though it's still relatively stable, right? And then with the primary, right, you can see the difference. Let me write that differently too. Oh, come on, Russell. All right. So that's why this method is specific for tertiary and secondary carbocations. I mean, tertiary and secondary alcohols, because during the process of the reaction happening in the mechanism, you lose that leaving group and you're going to make a carbocation. So that carbocation intermediate, it kind of drives the whole reaction, because this is the rate determining step. That's the rate determining step, loss of leaving group. And this is the mechanism. It's what we call an SN1 type mechanism, where the leaving group leaves first, and then the nucleophile comes in and does the substitution. All right, questions about that? Let me write that up here. Right, and this is for the substitution part. So this part right here, the proton transfer part, is not the rate determining step. The substitution happens between the loss of your leaving group and then the addition of the nucleophile. So it will be this step followed by that step. That's going to be my substitution part. So that's why I care about like carbocations and intermediates and all that stuff, right? So now we have the carbocation, and over here, I just have it drawn with iodine, right? So iodine just needs to attack the carbocation, the plus charge, and that'll give me my product, right? Which is an alkyl halide, right? So for this reaction, the first thing you have to do is convert alcohol into a better leaving group, And then the intermediate that you get from that intermediate gets converted into a carbocation, which then gets attacked by iodine. Sorry. All right. Any questions about anything that we just talked about? All right, let's look at that next example down underneath it. And this example is kind of like a question designed to make the point we made up top. Right, so it's designed to make the point about why secondary, why it's specific for secondary and tertiary, right? So let me put that up here. So why would it slow down if you use the primary? I'm gonna mark this out. All right, let's answer that question. What do you think? What's the first thing that's going to happen here? Based on what we just looked at, it's the same reaction. It's just on a different substrate. So what do you think the first thing is going to happen?
Make OH a better leaving group.
Make it a better leaving group by what process? What are we doing in this case?
Proton transfer.
Proton transfer. Good. So I'm going to do this. Let me make that a little thinner. I'm going to do this. So that's going to pick up the proton. And then let me put my lone pairs in here. I'm going to lose chlorine. All right, so that's going to give me, and I'm going to draw those carbons out. It's going to give me this, isn't it? Is that right? Plus what?
Cl minus.
Plus Cl minus, good. Right, and then this will equilibrate between itself and hold up. No. One more carbon on there. And this, let me show that this is a CH2 with a plus charge. What's the problem here? Why do you, again, let's go back to the original question. Why would the reaction slow down for a primary alcohol?
Is it less stable?
Yes. What's less stable though? Which part?
Where the CH2 is?
Yes. So this is a much, that's excellent. Less stable carbocation, which means that the leaving group will leave much slower, right? We asked the question, why would it slow down? And what do we know about the loss of leaving group for this particular reaction and this mechanism? What do we know about that step? based on what we just talked about up top.
It's the rate determining step.
Determines the rate. So if I slow down the rate determining step, then the whole reaction is going to slow down. Right? So I'm gonna slow, if I slow that rate determining step down, the whole reaction slows down. Right? We don't even have to show the product formation because that's not gonna help us answer that question. Now, here's another question. Normally, if you have a primary alcohol, the mechanism, instead of it trying to go SN1 and making a carbocation, more than likely that mechanism is going to switch to a SN2. All right, so let me just put that down here too. All right, it'll also, and we'll talk about SN2 in the next, with the next mechanism we study. All right, any questions about that, about this?
Can you repeat what you said about it going to SN2, please?
Yeah, so it's possible that the reaction, let me expand that. And let me write this out in a little bit more cogent terms. Right, so it's possible that for it to go via SN2, let me not say that. I'm gonna say to avoid. Right, so it's possible that it'll go SN2 to avoid that carbocation intermediate. I'm gonna highlight that. All right.
Okay, thank you.
That's a possibility, but it's still going to be slower than a tertiary, which is going to fly compared to a primary, because making a tertiary carbocation is, you know, is really, that's good because it's a really stable intermediate. And again, everything in chemistry, 99% of the time is going to be dictated by stability or lack thereof. All right. Any questions about this reaction? All right, let's do the next method, which is to use PBr3. And this method is here. And this method is specific for primary and secondary alcohols. Can you take a guess as to, not an educated guess, as to why or what type of substitution mechanism this goes through, if it's specific for primary or secondary, based on what we just talked about down below? Well,
SN2?
yes, the substitution is going to be more of a SN2 type mechanism than an SN1 type mechanism. All right, great, that was great. All right, let's look at the reaction. What is, so we're just gonna use some logic. We're gonna look at the intermediate right here, which is the product from the first reaction. And you tell me what happened. Like, how did I get to that intermediate? Anybody? What does it look like happen in the intermediate? What do I have over here?
Would it be a proton
ahead.
transfer?
No, not in this case. Not in this case. Proton transfer only happens when you have a acidic proton somewhere that's given to another atom through an acid-base reaction, right? So I need an H plus somewhere. So I don't have a proton transfer here, but can you see I have a new bond between P and O that I didn't
Yes.
have on the left side of the arrow?
Mhm.
So let me ask this question, because this is really important. How do I know, like, how do I show a bond being made between two atoms? What do I use?
Is it a two-sided arrow?
A two-sided arrow coming from one molecule or coming from my donor and going to my acceptor. Is that right? Or coming from my nucleophile and going to my electrophile. So in this case, oxygen is my nucleophile, and then PBr3 is all this is for part one. Nucleophiles, electrophiles, double-sided arrows, single-headed arrows, all that stuff we learned in part one when we studied our mechanisms. Right? So where's the arrow going to start? Does it start at the electrophile or the nucleophile?
The oxygen is gonna attack the phosphorus.
Yeah, this is coming here, right? And in the process, I'm going to lose bromine. And then, so over here, I can see how that oxygen phosphorus bond formed. I can also see how bromine got lost, right? Because I have a Br minus right here. That is going to become my nucleophile, right? So now on this step, this is the nucleophile. This is the electrophile. Now look at what happens, right? What would be the leaving group in this case? Because this is where the substitution part happens. Going from here to here is a substitution. What's my leaving group?
Bromine.
In this, and going from this step to this step, look at what I have over here.
Oxygen.
It's that whole thing.
The whole functional group, right? Can you see that? So this whole functional group is going to leave. Need more room. Right, that whole group is going to leave. So this bond, this CO bond right here, I'm cleaving that. I'm breaking that. Right, that's the bond I'm breaking. And the way I'm going to break it is to attack that carbon with bromine. All right, so this is going to come in. Let me erase all this other stuff I don't need. This is coming here because it is my nucleophile. Boom, like that. And then I'm going to break the CO bond by giving that pair of electrons to oxygen. Anybody not see that?
How is that like different from kind of what we just did? Because I know we said that when it's like plus CH2, so it's like less stable. But
Yeah. So
isn't
this
that kind
is,
of what just happened?
so this, that's a great question. So this substitution step is concerted. What it means is that the leaving group, as the nucleophile is coming in, the leaving group is leaving at the same time. In the last reaction, the leaving group left first, and then the nucleophile came in. So that would be considered, and I didn't mention that. I neglected to mention that, but let me go back down here. Right, this substitution would be considered stepwise. Right, I think I did. Yeah, I had to put it right here. I'll put it here. Right, so this is stepwise. Leaving group leaves first, and then the nucleophile attacks. Up here is concerted, which means that the nucleophile is approaching as the leaving group is leaving. So they're leaving simultaneously. I'll say it like this: nucleophile approach and leaving group departure are simultaneous. That's the difference in a stepwise reaction mechanism and a concerted. So the stepwise, like if you think about it in overall terms, all reactions mechanisms are stepwise because they happen in multiple steps, right? Unless it's just a single step. But when we kind of zoom in on the substitution step can be either concerted, whereas the substitution happens all at once, like in this case, or it can be stepwise, whereas even the substitution part is broken down into two steps, where you lose your leaving group first and then your nucleophile attacks. All right, did that answer your question?
Yeah, that makes sense.
Okay, so then once I attack the carbon oxygen single bond, I have my product, and you can see that bromine has now replaced oxygen, right? In a substitution reaction. Oh, I forgot, I made that thinner. Right, you can see that bromine has replaced oxygen in a substitution. All right, this is again specific for primary and secondary alcohols. And one of the things about this reaction that's kind of neat, well, I don't want to say neat, that's an old crusty term. That's important is the stoichiometry, right? It's always 3-to-1 alcohol to PBr3. Because if you look at the side product over here, I still have 2 bromines left. So that means I can do 2 more reactions with that. On the same alcohol or on another molecule of alcohol. Does that make sense?
Yes.
So I could take this PBr3 or PBr2OH and react it with another molecule of that alcohol. I hope that's enough carbons. And I would get this. Plus P OH, BR through the same exact same mechanism. And then I could take this and react it again with another molecule of alcohol. And then I would get this plus POH3. Should put that in a different color. That's all right. All right. So when I use PBr3, my ratio of alcohol to my brominating agent is always going to be 3-to-1, because I can get 3 reactions out of 1 PBr3. Questions about that part? If you look at after the first reaction, the first cycle of the mechanism, you see I have a phosphorus with 2 bromines left on it. So I can take that and react it with another alcohol. And then now I have a phosphorus with 1 bromine left. So I can take that, react it with another alcohol, and then until I get to phosphorus with no bromines left. So here, that's when my reaction is done for that molecule of PBr3. All right, questions about that mechanism or that reaction? And on Wednesday, we're gonna see like different reactions and with the reagents over the arrow, so we can predict products and things like that. But right now, we're focusing on the mechanism, like how the reaction actually works.
I have a question.
Go right ahead.
So is it going to keep going until all the bromines are used up?
Yes.
Okay.
That's exactly right. All right, other questions about anything?